The hidden framework of the universe. Imagine a universe made mostly of something we cannot see, touch, or detect directly. Yet it controls everything. Galaxies spin because of it. Clusters bind together through it. Even the shape of the cosmos depends on it. That something is dark matter, and its invisible structures, called dark halos, are the scaffolding of the universe. When astronomers first measured how galaxies rotate, they expected the outer stars to move slowly, obeying Newton's laws. But they didn't. Instead, galaxies spun as if held together by an unseen mass extending far beyond their visible edges. Vera Rubin's work in the 1970s provided the first clear evidence. Rotation curves stayed flat, not declining. Something massive, transparent, and gravitationally dominant was at play. These invisible cocoons, later called dark matter halos, are not small clouds around galaxies. They are immense, spherical regions stretching hundreds of thousands of light-years, outweighing the visible parts of galaxies by a factor of 5 to 10. They are not just containers, they are architects. Every galaxy you can see, from the Milky Way to distant spirals captured by the James Webb Telescope, formed inside one of these halos. Without them, the universe would look utterly different, chaotic, structureless, almost empty of galaxies. Dark halos are made not of atoms or light, but of particles that interact only through gravity. Perhaps WIMPs, weakly interacting massive particles, axions, or something even stranger. We have never detected one directly, yet their fingerprints are everywhere. Galaxy motions, lensing of background light, and the large-scale cosmic web. It's as if an invisible skeleton holds the cosmos together, and we've only recently begun to map its shape. The birth of dark halos. After the Big Bang. To understand dark halos, we must rewind the clock to the very beginning. The universe started 13.8 billion years ago in an incomprehensibly hot, dense state, the Big Bang. In its first fraction of a second, matter and energy were almost perfectly uniform, but not entirely. Tiny quantum fluctuations, differences in density smaller than 1 part in $100,000, appeared in the cosmic plasma. As the universe expanded and cooled, dark matter decoupled from radiation earlier than ordinary matter. While photons bounced around in the hot plasma, dark matter moved freely, forming the first gravitational wells. By the time the cosmic microwave background, CMB, formed, about 380,000 years later, these dark wells had already started pulling more dark matter toward them. These were the first proto-halos, the seeds of all future galaxies. At that time, no stars, no planets, not even atoms as we know them existed. Hydrogen and helium gas floated in vast cooling clouds, but they could not collapse alone. They needed gravity's extra pull. That extra pull came from dark halos. Modern computer simulations, such as Illustris, Millennium, and Eagle, recreate this process in exquisite detail. They show how, within a few hundred million years after the Big Bang, dark matter formed web-like filaments, a cosmic sponge of dense nodes connected by vast voids. Gas streamed along these filaments, settling into the densest knots, dark halos. In these knots, pressure and cooling allowed baryonic matter, the ordinary atoms, to form the first stars, galaxies, and later, galaxy clusters. The halos themselves grew through accretion, pulling in more dark matter and merging with others. This process is hierarchical. Small halos form first, then merge into larger ones. By 1 billion years after the Big Bang, the first dwarf galaxies glowed faintly inside halos 1 billion times the mass of the Sun. By 2 billion years, halos 1,000 times larger hosted massive spiral and elliptical galaxies. It's a grand cosmic construction project, and dark halos are the blueprints. Baryonic matter joins the dance. Dark matter does not shine, but it creates the stage on which light can finally appear. As halos grow, they begin attracting normal matter, gas composed mostly of hydrogen and helium. Unlike dark matter, baryonic gas can collide, compress, and cool. When it falls into a halo's gravitational well, it heats to millions of degrees, then slowly cools. condensing into disks and forming the first stars. This is where visible galaxies emerge. The Milky Way, for example, sits inside a halo roughly 1 trillion solar masses in total, while its stars account for only about 5% of that mass. Everything we see, the spiral arms, nebulae, and star clusters, is just the glowing skin of a vast invisible structure. Simulations reveal that baryonic matter doesn't just fall straight in. As it spirals inward, it gains angular momentum, creating rotating disks. These disks form stars in waves, while supernova explosions push gas back out, balancing inflow and feedback. Yet even these violent events cannot destroy the dark halo's gravitational framework. It remains stable, holding the system together over billions of years. Interestingly, the amount of gas that can cool depends on the halo's mass. If the halo is too small, supernova winds can blow the gas away, preventing star formation. If it's too massive, the gas becomes too hot to cool efficiently. Only halos in a certain mass range, about 109 to 1012 solar masses, can form galaxies similar to those we observe today. Dark halos therefore act as cosmic regulators, determining not only where galaxies form but also what kind of galaxies they become. Every galaxy's shape, mass, and even its ability to host life traces back to its invisible dark foundation, halo growth, and hierarchical merging. As the universe ages, dark halos don't remain static. They grow, collide, and merge, a process astronomers call hierarchical structure formation. This idea reshaped cosmology in the 1990s. Instead of giant galaxies forming first, small halos coalesced to build larger ones. In early cosmic epochs, the universe was a playground of small halos, tiny gravity wells barely massive enough to hold a few million solar masses of dark matter. Over time, gravity pulled these halos together along the filaments of the cosmic web. When two halos met, they merged, their dark matter clouds interpenetrating and settling into a single, larger structure. Each merger sparked new astrophysical drama. Gas trapped in the merging halos collided and compressed, triggering starburst events. Brief, furious periods of star formation. The merging process also altered galaxy shapes. Disks were torn apart, forming ellipticals. Smaller companions were absorbed, forming bulges and stellar halos. Computer simulations like Millennium, Bolshoi, and Illustris TNG illustrate this process beautifully. They show a universe where halos are like bubbles, coalescing in a cosmic foam, connecting through filaments that span billions of light years. The densest knots, supermassive halos, host galaxy clusters containing hundreds or even thousands of galaxies. When a smaller halo merges into a larger one, it often survives as a subhalo, orbiting the central mass for billions of years. Each subhalo may carry its own dwarf galaxy. Satellite systems like the Magellanic Clouds around the Milky Way are perfect examples. These remnants tell us about the violent growth history of their host halos. Observations from the Sloan Digital Sky Survey, SDSS, and Gaia mission show that our Milky Way halo still contains streams of stars, fossils of ancient mergers. Each stream marks a smaller galaxy that once plunged into ours and was gradually shredded apart by gravity. This cosmic cannibalism is not chaos. It's structure formation in action. The universe, at its grandest scale, is a vast machine that builds complexity through collisions. The invisible influence, rotation, shape, and stability. The visible shape of a galaxy, spiral, elliptical, or irregular, isn't merely aesthetic. It's an imprint of its halo's mass, spin, and history. In a spiral galaxy, the dark halo provides the gravitational glue that keeps the disk intact. Stars in the Milky Way rotate around the center at 220 km/s, yet the visible mass of the galaxy isn't enough to hold them in orbit. Without the surrounding halo, the outer regions would simply drift away. Dark halos maintain the flat rotation curves, a feature confirmed in thousands of galaxies. Halos also influence galaxy morphology. If a halo forms with significant angular momentum, gas falling into it flattens into a rotating disk, producing a spiral galaxy. If the halo forms through frequent mergers, that rotation is disrupted, leading to a spheroidal or elliptical galaxy. And if the halo is small or irregularly shaped, the galaxy becomes a chaotic, irregular type. Even more intriguing, the density profile of halos, described by the Navarro-Frank-White (EONFW) model, affects how stars and gas distribute within. A concentrated halo produces a tightly bound core. A diffuse halo allows a more extended disk. Recent observations by the James Webb Space Telescope, JWST, and the Atacama Large Millimeter Array, ALMA, confirm that galaxies already possessed well-developed disks just a few hundred million years after the Big Bang. This means that halos were already spinning rapidly at early times. A surprising revelation for theorists who once thought disks took billions of years to settle. Dark halos also explain why galaxies of vastly different brightness can have similar sizes or rotation speeds. This relationship, called the Tully-Fisher relation, arises because the halo's total mass determines the gravitational potential, and therefore the velocity of rotation, more than the visible mass does. But dark halos do more than govern motion. They provide stability. Without the cushioning of a massive halo, galaxies would be torn apart by their own dynamics or tidal interactions. The halo acts like a cosmic shock absorber, protecting the luminous core from gravitational harassment by neighbors. Even satellite galaxies orbiting a larger system survive because of their miniature halos, collisions, interactions, and evolution. In the universe, collisions are inevitable. Unlike in our daily lives, cosmic collisions rarely involve direct contact. They're gravitational encounters, slow and spectacular. When two galaxies approach, their dark halos meet first, long before the visible stars interact. As halos overlap, they begin to merge, exchanging orbital energy through dynamical friction, a drag force that causes galaxies to spiral closer over billions of years. This invisible dance reshapes both systems. Take the upcoming Milky Way-Andromeda collision, predicted to occur in about 4 billion years. Their halos are already interacting. Dark matter from each galaxy has extended so far that they're essentially touching. When the visible parts finally meet, tidal forces will stretch them into elongated streams, and gas clouds will compress to ignite starburst regions. After a few billion years, the two spirals will merge into a single, massive elliptical galaxy. Yet the dark halo will remain intact, merged, enlarged, and still invisible. The role of halos in such events cannot be overstated. They dictate how much energy is lost, how long mergers take, and what the final product looks like. Simulations show that halos with more mass or more extended profiles lead to longer, slower mergers, often producing larger, more diffuse ellipticals. Galaxy clusters are extreme examples of this process. The Bullet cluster, for instance, provides one of the strongest proofs of dark matter's existence. When two clusters collided, their hot gas, visible in X-rays, slowed down and separated, but the bulk of the mass, traced by gravitational lensing, passed straight through. That mass corresponds to the dark halos, unaffected by collisions because they barely interact except through gravity. Every collision leaves fingerprints in the halos. Streams of dark matter, subhalos, and shells ripple through the merged structure for eons, influencing how future stars and satellites form. Even after galaxies settle into quiet adulthood, their halos continue to accrete material, slowly pulling in intergalactic gas, dwarf galaxies, and dark matter clumps. In essence, a halo is never finished. It grows, digests, and evolves, like a living organism on cosmic timescales. The interplay between visible and invisible matter determines the fate of galaxies. Star formation rates rise and fall depending on how efficiently gas can cool within the halo. Supermassive black holes at galactic centers feed on that gas and, in turn, release enormous energy, sometimes powerful enough to heat or expel gas, quenching further star formation. But the halo remains, holding the remnants together, guiding the next cycle of cosmic creation, the future of research and cosmic mysteries. Despite decades of study, dark halos remain partly mysterious. We know they exist, but we don't know what they're made of. The next generation of experiments and observatories aims to answer that question. On Earth, facilities like Xenont, Lux Zeppelin, and Super CDMS attempt to catch the faintest hint of dark matter particles colliding with atoms. So far, the results are silent, but silence itself narrows the field, ruling out certain candidates and guiding theory. In space, observatories such as JWST, Euclid, and the upcoming Vera Rubin Observatory, with its legacy survey of space and time, are mapping billions of galaxies, measuring how dark matter bends light through weak gravitational lensing. By comparing these cosmic distortions, astronomers can trace the three-dimensional shape of halos across billions of years of history. These surveys already reveal something profound. Dark halos form earlier and grow faster than we once thought. Some galaxies in the early universe are too massive for their age, suggesting that dark matter may have begun clustering even before our models predict. This challenges the standard LCDM, lambda cold dark matter, cosmological model, hinting that dark matter could be warmer, self-interacting, or composed of multiple particle species. Meanwhile, simulations are reaching new levels of realism. Projects such as Illustris, TNG, Eagle, and Fire 3 include feedback from supernovae, black hole jets, and cosmic radiation. They show how delicate the balance is between gas inflow and feedback, and how halos regulate both. Without halos, feedback would simply blow gas into space. With halos, galaxies retain enough material to keep forming stars for billions of years. Even the faintest, smallest galaxies we can detect, the ultra-faint dwarfs orbiting the Milky Way, reveal dark halo secrets. They contain very few stars but enormous amounts of dark matter, making them ideal laboratories for studying how halos behave at small scales. These dwarfs suggest that dark matter is cold, moving slowly enough to clump efficiently, but not perfectly smooth. Their distribution challenges simple predictions, implying that dark matter could have subtle interactions or quantum properties. And then there are the cosmic what-ifs. What if dark halos can collapse without forming stars, remaining truly dark galaxies? What if some halos contain massive black holes but almost no visible matter? Astronomers are already searching for such dark galaxies through their gravitational lensing effects and hydrogen emission signatures. Understanding dark halos isn't just about galaxies. It's about understanding the architecture of the universe itself. Every cluster, filament, and void is defined by the way dark matter shaped space-time. Even the expansion rate of the universe depends on how these halos grew under gravity versus how dark energy stretches the cosmos apart. As our instruments improve, we may soon see indirect clues about the very nature of dark matter, perhaps in tiny fluctuations of the cosmic microwave background or faint gamma-ray glows from annihilating particles. Each piece of evidence will refine our picture of these vast, invisible structures that have silently orchestrated cosmic evolution since the dawn of time. And yet, perhaps the greatest mystery remains philosophical. If 85% of the universe's mass is invisible, then what we call the visible universe is merely a trace, a luminous frosting on a dark cosmic skeleton. Conclusion: the invisible architects of the cosmos. From the first flicker after the Big Bang to the majestic spiral of the Milky Way, dark halos have been there, quietly shaping everything. They formed before the first stars, guided the birth of galaxies, and continue to sculpt the universe's large-scale structure. Though we can't see them, we feel their pull. Every orbiting star, every bending beam of light, every merging cluster whispers the same truth. The cosmos is built not on what shines, but on what hides. In the next decades, as telescopes and detectors probe deeper, we may finally uncover the identity of the particles that compose these halos. But even if we do, one thing will remain certain: the story of galaxies, their birth, growth, and destiny, can never be told without the dark halos that cradle them. The universe, in all its brilliance, is written in the language of darkness.